Anybody who's involved in phased array radar systems or phased array antenna systems, digital beamforming, they're all using multiple parallel transmit and receive channels to deliver their solutions. And you have to achieve synchronization across those channels. And if you're talking about large parallel number of channels, you're talking big systems, you're talking backplane oriented systems, and routing the clock and the signal throughout those systems is really, really challenging. And there's not a lot that's around that helps designers solve that headache. So we're really excited today. Teledyne E2V, we think we've cracked it. We have a feature in our latest products that we call sync chaining. The sync chain is a single pulse, 5 to 10 nanoseconds in length, which is quite a significant order of magnitude larger than the wavelength of the signals that we are interested in. The benefit to the designer of the system is that this is a signal that's a lot easier to send throughout the system, and it really facilitates a very easy way of precisely determining when the sample process is to take place. And the clear benefit here is that now we preserve the all-important signal phase information in which we can then work out, the spatial information from that. With the sync chain, it's sourced from the signal processing block. It's not an advanced precision clock source, so it's easy to route. But when the sync chain emerges from one ADC in the chain, it is forced to be synchronous to the master sample clock. And this means that theoretically, you can have an infinite chain of ADCs connected with a guaranteed synchronization edge. Once the system is set up with sync chain, it's good to go. You train the system once when you have your final prototype, and you can guarantee whenever you power the system up, whenever you power cycle the system, if the environment changes, the parts will still be synchronized. That's the big breakthrough here.
In our lab, we have a demonstration setup consisting of two EV12AQ600 ADC boards connected together to an FPGA for signal processing. The demo represents the real-life system like you would have in phased array antennas employing digital beamforming or MIMO system approach. As we look through the setup, we have a signal generator that generates the master clock signal at 6.4 GHz. We have a second signal generator that generates the input signal for the demonstration. In order to monitor the signal coming out from this signal generator, we have an oscilloscope on which we can see the square waveform coming out of the signal generator. So we have the two boards connected together only through the sync signal cables. The two boards are connected to the clock generator with cables having the same length. On the input of the two boards, the cables are also of the same length in order to have the same phase of the signal arriving at the input of the ADC boards. We also have a screen to show the output waveform coming from the ADCs. The sync signal comes from the FPGA and is sent to the first ADC so that the first ADC can be synchronized. The output waveform from the ADC1 is plotted, whereas the second ADC doesn't output any waveform. If we activate the synchronization chain register, the sync out, the synchronization pulse can propagate directly from the first ADC to the second ADC in a deterministic manner and synchronously to the master clock. The output waveforms show some phase delay, obviously linked to the propagation time between the first and the second ADC of the sync signal. This coarse phase shift can be adjusted by increasing the number of samples up to here 7, corresponding to the number of samples. For the fine phase delay adjust, it can be controlled by the sync control register in order to add up to 4 phases of the master clock. Once the phase delay is identified and corrected, the system, once set, will be rock solid under all conditions, and you can confidently go to mass production of your prototype. If we change the physical configuration of the system, if we retrain it and reassert the sync, we can still see the phase alignment between the two ADCs. There are 3 points that helps to demonstrate the robustness of the sync chain approach. The first is that there is no variation over temperature. By removing the heat sink, we can see the increase of the temperature of the ADC itself. There is still no phase delay between the two waveforms. Even removing the clock signal from one of the ADC and plugging it again, we can see that just resyncing enables to still have phase alignment between the two ADCs. By powering off and on the system and resetting the ADC in the initial condition or the conditions obtained during the training sequence, we can still obtain the same phase alignment between the two ADCs. So this test proved the robustness of the ADC synchronization through the synchronization chaining in a deterministic manner, as well as ADC synchronization in a very challenging layout environment.
We've demonstrated sync chaining works. It works over environmental changes such as temperature. We've shown that we can save system cost. We have eliminated what is a complex challenge of calibrating systems, which has big impact on manufacturing. And perhaps most importantly, we've given back control of the time domain to developers. And we're really excited to see what you can do with it.